Hello everyone, in this module we're going to continue on with the third concept as to why our energy levels of our orbitals are not equal. So we've already went over Coulomb's law and shielding. Finally, we're going to end with penetration. Now with penetration, I'm going to go ahead and draw our lithium over here. Remember our lithium, it had a +3, and then let me go ahead and draw a ring around there. Okay, so we know that it had 2 core electrons, so I'm going to use a different color for my core electrons. So here I have the 2 core electrons, and then over here we had the valence electron. So imagine that this valence electron can come really close to the nucleus, so it could feel this full +3 charge, okay? So if it experiences a greater nuclear charge, if you recall, that means it's going to have a lower energy, and if it has a lower energy, it means it's more stable. Okay, well, how can it do this? Well, there's something called the penetration effect. Now, some orbitals, they have the ability to penetrate into the space of the core orbitals. Why do they do that? It's due to the difference in the wave functions and the shapes of the orbitals. So I'm going to go ahead and start with the radial probability graph over here on the left. We went over this in chapter 7, but again, it shows the total probability of finding an electron within the spherical shell at the distance r from the nucleus, right? So the 1s is way up here, and we know that the 1s is going to be closer to the nucleus than here's the 2s and the 2p. So there's something that I want to point out about this 2s now. Let me go back with this color. Now 2s is in the red. Notice that we have 2 areas. So we have here, I'm going to color that in. We have this little hump, and then there's our node, and then we have this area under the curve as well. So if we take the sum of these 2 areas, we add the area under the curve. This little bump here, by having this little bump, it shifts our probability of finding that electron closer to the nucleus than just an electron in the 2p orbital. Again, if it's closer to the nucleus, it means it's lower in energy. Now that's all because of this little bump right here. So all because of that little bump, the 2s orbital has the ability to get into the space of the 1s orbital. Okay, so it's getting really close to the nucleus. Now let's go ahead and look at this graph over here. So notice here all the ends are n equals 3. So we have our 3s, our 3p, and our 3d. So our 3s electron, let's look at that here. So 3s is in purple. So let me try to get I don't really have a purple color up here. I guess I don't want to waste time trying to find it. So I'm just going to go ahead and take a look here. So here's 3s. So here's our big part for 3s. Then here's the other. It has 2 little bumps. Okay, hopefully you remember that from the last chapter as well. But here our 3s electron is actually going more deeply into those inner orbitals because of the 3 areas under the curve here. Now, it's experiencing it's experiencing the greatest effective nuclear charge compared to the 3p and the 3d. Now 3p, as you saw here, the 3p has 1 little bump. So it's experiencing a greater effective nuclear charge than the 3d. So 3s experiences the most. 3d has the least penetration. Now, why is this important? This accounts for the ordering of our sublevels. So here our S, this should be like this. Our S has a lower energy than our P, which is lower than our D. Now, again, this is important because of penetration. Our sublevels in the principal energy level n equals 3 are not degenerate. They don't have the same energies. Okay, so I hope that makes sense. And that's going to complete this module, but we are going to focus on the next module with electron configuration again.